of graph isomorphism. Please, go ahead.
Yeah, thanks. Thank you for being here, and thanks to the organizers for giving me this opportunity. I want to tell you about a specific project, about a class of non-local games that is based on graphs. But before I do so, I want to give you a glimpse of sort of a bigger picture, where I would like to propose sort of non-local games as a nice and structured way to study quantum entanglement. All right, so we all know, right, that quantum entanglement is one of the key quantum features, and in fact, it's behind many of these quantum advantages that we as a field are after. And of course, quantum entanglement is a property of composite systems, so you can talk about entanglement if you have some big quantum system, which is composed of smaller quantum systems. And now you can think of these smaller quantum systems as belonging to sort of different agents, which maybe are trying to accomplish some information processing task. All right, and we know that entanglement is not going to let these agents to send information to one another. However, these agents, they can take advantage of entanglement by performing some sort of measurements on their parts of the entangled state, and then using these correlations that they get as a result in order to do some task, right? And we know that these correlations that they can get are stronger than classical ones, so they form a superset of the correlations that they could get classically. And this lets them to correlate their behavior sort of beyond the classically reachable limits. And now they can use these stronger than classical correlations to do some interesting things. So for instance, I'm just going to mention few things, all right, a disclaimer, just a few applications of entanglement. By no means this is an exhaustive list, and not an exhaustive list of references either. There wouldn't be place on one slide for all of them. So first we can use entanglement to get improvement for communication, right? So here your agents, they want to send some sort of information from one to another. And this improvement that we get, it could be quantitative or it could be qualitative. So qualitative, that would mean that entanglement lets us trade certain more expensive kind of communication for a cheaper one. And here the teleportation protocol that probably all of us know is an example, right? It lets us trade quantum communication for classical one using entanglement. And the second example is superdense coding. So here we are getting quantitative advantage. So we are doubling the classical capacity of some quantum channel using entanglement. And a second kind of broad area of application of entanglement is that of device-independent cryptography. So here we are using entanglement in order to ensure proper functioning of our quantum devices. So entanglement sort of lets us devise these protocols which we can run securely even if we don't trust the devices. Right? It's kind of counterintuitive that this is possible at all. And finally, we can use entanglement to study things like black hole dynamics. Like you take an entangled state, you throw half of it in a black hole, and then you look at the paradoxes that arise from that. All right, so these are all kind of very nice examples of how we can use entanglement and what cool things we can do with it. However, I want to say that actually we don't understand entanglement that well. So if you have some kind of distributed information processing setting with some agents, and you ask, okay, what happens if I give them entanglement? Is it going to give some advantage, and how big this advantage is going to be? Like nobody is going to be, in general, nobody is going to be able to tell you, right? And one of the reasons is just if you write down the mathematical problem, it's very complicated. So we need some, of course, if we ever want to kind of fully harness this power or this things that entanglement has to offer to us, right? We need to understand it, right? That's kind of the first step. And I would like to, sort of as a possible line of attack for better understanding quantum entanglement, I think non-local games give us a nice and structured framework where we can actually prove things on one hand, and on the other hand, actually a lot of these applications of entanglement, especially say the second one of secure protocols, the device-independent protocols, so those come out of non-local games, right? They're kind of powered by non-local games. And these non-local games, they already appear in kind of various fields of study, and that's also very nice. They are known by different names, though, in different areas. So first in computer science, they would correspond to multiple prover interactive proof systems. And the study of such proof systems actually has led to one of kind of the biggest or one of the most significant results in complexity theory and maybe even theoretical computer science as a whole, the so-called PCP theorem. And then lately, non-local games have been used in cryptography to kind of make these device-independent protocols that I mentioned before. And of course, they also appear in physics. And there they would be known as Bell inequalities or Bell setups, I guess, and Bell inequalities and their violations. And then we can trace the origins of these non-local games back to the Einstein-Podolsky-Rosen paradox, right, and the response to it by John Bell, who proposed this experimental setup where we could test whether or not this spooky action at a distance that Einstein so much disliked is real or not, right? And nowadays, of course, we have resolved this problem, and we've seen many experimental demonstrations, and I just want to mention one which was closing all the sort of most common loopholes at the same time, and that happened in 2015. All right, but what is a non-local game? I hope that most of you actually know, but it never hurts to repeat, so let's see. So here this is the most basic form of a non-local game, all right? You can think of different variants. So here you have two players or provers, Alice and Bob are friends. They are gonna work together. They're together gonna win or lose this game, okay? And then you have a verifier, right? He's somehow checking and announcing whether Alice and Bob win or lose. So the game starts when the verifier selects two questions from some pre-specified sets. And he selects these questions according to some known probability distribution pi. So he picks S and T according to pi. He sends S to Alice and T to Bob. And then Alice and Bob need to respond with some answers, again, from some pre-specified sets. And then after receiving the answers, the verifier is going to announce whether Alice and Bob lose or win the game. And he's going to do so according to this verification function V, which maps sort of question-answer pairs to 0 or 1, or lose and win. Okay? And in this setting, sort of the game is specified by this verification function V and the probability distribution pi. And everybody knows the V and the pi. So the rules of the game are known. What makes it complicated is that Alice and Bob, they cannot talk to each other after they have received these questions S and T from the verifier. Okay? They can meet before the start of the game. They know pi and they know the rules of the game, the V. And they can agree on some strategy that they're going to use in order to try to maximize their chances of winning. So that's the goal of Alice and Bob. They want to win, right? Nobody likes to lose. So, and then the quantities that we look at is first the highest possible classical success probability for a given game, and that's often denoted by omega of G. G is a game. And we contrast that with what is possible when we allow quantum strategies, okay? And the corresponding success probability denoted by omega star. So the game remains the same in the quantum case as well. All that changes is sort of the strategies that Alice and Bob have access to. All right. So now this is the most basic form of a non-local game. You could think of variants where you have more players. So you maybe have Alice, Bob, and Charlie. Or you could think of the cases where the verification function is more complicated, or maybe the questions are not classical, but they are quantum states. many different variants. All right, but now, if we model our operational or cryptographic task that we want to do with our distributed agents as a non-local game, then this question, right, that we are interested in, when can entanglement be helpful for information processing, that turns into simply asking if omega star exceeds omega. And if we want to know how helpful is entanglement, then that would correspond to understanding the difference or the ratio of the two quantities. And just a little bit of a warning is that, of course, things are not so simple, and answering these questions, is omega star greater than omega, or how large is omega star minus omega, they are hard questions. And so as we suspected that it's very hard to determine this quantity omega star, and recently in a breakthrough result, William Sloster has shown that indeed this omega star is not computable. So the classical quantity omega, that one is NP complete to compute, so it might take a long time for us to actually compute it, but we can compute it. In the quantum case, things are much worse. Sort of there's no algorithm whatsoever that's going to tell you the value of omega star. And we also don't know how to approximate it efficiently. Okay, so this is where I want to end the kind of big picture things. So just as a summary, so I want to say that non-local games gives us sort of a structured framework where we can sort of explore the capabilities and also the limitations of entanglement, right? On one hand, and on the other hand, they sort of provide interesting protocols or give us interesting applications of entanglement. All right. And now I want to move on to telling you about a specific class of non-local games that we looked at together with my co-authors. So Albert, David, Robert, Simone, and Antonis. And this is going to be a very, very special class of non-local games. So not every non-local game takes this specific form. And instead of asking what is the best success probability that quantum players can achieve, I'm going to be asking whether or not there exists a quantum strategy which allows quantum players to always win. Okay? So this is a very specific question. However, kind of making things more specific is going to endow these strategies with some additional structure. And it's going to allow us to make connections to other areas of study, such as descriptive complexity or optimization, logic, and category theory. So the idea is that this class of games could help us exhibit some extremal behaviors of quantum entanglement. And on the other hand, it could provide us with some nice protocols where we can observe quantum advantage. All right, now let's jump into it. So the games are based on graphs. This is an example of a graph. So we have some vertices, we have some edges. Now graph isomorphism, the idea is that the two graphs are isomorphic if it's actually the same graph, right? But maybe I've labeled the vertices differently, so it's not obvious at first sight that graphs are isomorphic. So here is an example, right? For this graph, you probably see it's actually the same graph, both on the left and the right. But now, if my graphs are bigger, it's not so easy. It's not so easy to tell whether it is the same graph or not. Okay, that was just kind of hand-wavy explanation. Now, formally, graph isomorphism is a function, right, which takes vertices of one graph to those of the other. And we want that this function is a bijection, so one-to-one, and it preserves both adjacency and non-adjacency, right? So if I take two adjacent vertices and map them, then I get two adjacent vertices in my target graph, and the same for non-adjacent vertices. All right, and so whenever such a mapping F exists, we say that graphs are isomorphic, and I'm going to denote it using this congruence symbol. Right now, another frequently used definition of isomorphism is in terms of existence of a permutation matrix. So, and I'm going to refer to this type of definition as like matrix-based definition of isomorphism. So here we have adjacency matrices of the two graphs, AG and AH. So adjacency matrix is just a way of describing a graph, right? So it's a matrix in whose rows and columns are indexed by vertices in your graph. the entries are 0 and 1, and you put a 1 wherever you have an edge. Okay, that's the adjacency matrix. So the two graphs are isomorphic if and only if you can find a permutation matrix P which conjugates the adjacency matrix of one graph to that of the other. And because permutation matrices are invertible, I can rewrite this equation in this sort of commutation-like manner. Okay. But now I want to have a non-local game. So I want to find a way how to think about graph isomorphism in terms of a non-local game. All right. The idea behind the game is that we have our provers, Alice and Bob, and they are going to try to convince the verifier that two graphs are indeed isomorphic. So how they're going to do that? So our three parties, the questions are going to be vertices. So the verifier is going to pick two vertices. They could be from either one of the graphs, or one could be from one graph and the other one from the other graph. He sends the vertex x to Alice and x prime to Bob. And Alice and Bob are going to respond with, again, with vertices, but they are required to respond with vertices from the other graph. So if a player gets vertex from graph G, they should respond with a vertex from H, and the other way around. If they got a vertex from H, they should respond with a vertex from G. Okay? Now, if they do this, then sort of after the verifier receives the answers, then for each of the players, right, one of the vertices is from graph G, one is from graph H. We don't know which one, right? It could be it's the X or the Y, let's say, for Alice. But there's exactly one vertex from each of the graphs among X, Y, and also among X prime and Y prime. And now the winning rule is the following one. Okay, and of course, Alice and Bob can't talk to each other after they've gotten this X and X prime. All right, and here's the winning rule. So in order to win, they need to ensure that the relationship between the G vertices of the two players is the same as the relationship between their H vertices. So remember, every player had one vertex from G, one from H. Okay, and this relationship could take one out of three different values. So the vertices could be adjacent, they could be distinct non-adjacent, or they could be the same. Okay? So for instance, if X and X prime were two vertices from H that were distinct non-adjacent, then in order to win, Alice and Bob need to respond with Y and Y prime from G that are also distinct and non-adjacent. Okay? Any questions about the game? I know it's a little bit complicated. But just remember, okay, it's like verifier sends out vertices, receives vertices as well, and then we're checking if the relationship between the G vertices is the same as the relationship between the H vertices. No, that's not the case. So X could be from G, and X prime could be from H. Now, if that is the case, then Alice needs to respond with Y from G, and Bob needs to respond with Y prime from H. Okay, I've lost track by this one. Okay, but so now X and Y prime are both in G, and they are related in some way. For instance, they could be adjacent. And then in order to win, it needs to be that Y and X prime are also adjacent, but now in H, because those are vertices of H. Okay, great question. So when I say relate, the relationship takes one out of three different values. So adjacent, distinct, non-adjacent, or the same. So I look at the vertices of the two players. I don't know if it's the question or the answer, but there is one vertex from G for each of the players. And I ask, okay, are they the same? Are they distinct, non-adjacent? Are they adjacent? It takes one value, and I require that the vertices from H of the two players, they are related the same way. So if the vertices were adjacent, they're adjacent. If distinct, non-adjacent, distinct, non-adjacent. Okay. Yeah? No, it's just one vertex. No path. Yeah. Yeah, I don't know anything about the distance. I only check if they are adjacent or not adjacent, or distinct non-adjacent. So if they're distinct non-adjacent, they could be distance 2, 3, 4, so on. Sorry? Yeah, yeah, exactly. We're not checking the distances. So this game would be actually trivial if the players send each other the questions, x and x prime, they got. So we don't let them talk to each other after they've gotten x and x prime, but they can talk to each other beforehand. So they know the two graphs, G and H, and they can meet and sort of decide how they're going to try to win this game. Okay, right. And now the question we want to ask, sort of, for which sort of pairs of graphs, G and H, can Alice and Bob win this game irrespective of the vertices received? So remember when I defined a general non-local game, I had this probability distribution on the questions. And here I don't have a probability distribution. And the reason why I don't have it is because I'm asking that the players can win with success probability 1. So I could put any probability distribution on this x and x prime as long as it had full support. Okay? So for these games, we sort of don't care about the probability distribution. We just say, is there a strategy that wins irrespective of the questions that the verifier selects? And from now on, I'm just going to say, can Alice and Bob win? And by that, I'm going to mean irrespective of the vertices received. Okay. Just to get a better understanding of the game and how things work, let's suppose that two graphs are indeed isomorphic, right? So there is this mapping F that takes vertices from one graph to those of the other, that is bijection, preserves adjacency, non-adjacency. Okay? Then what the players could do is they could play according to this isomorphism F. So if a player, before the game, they agree on this F, and then when they get their x or x prime, they respond with either f of x, if the x is in graph G, because f was a function taking vertices of G to those of H, or they respond with f inverse of x, if they got a vertex from H. And it's not too hard to see that this strategy is going to allow the players to win irrespective of the vertices that the verifier sent them. Okay, assuming you remember rules of the game. Yes. Okay, so I assume that the vertex sets are disjoint of the graphs. If you somehow label them the same, so I want Alice, when Alice or Bob gets the vertex, then they know which graph it comes from. So it's not, yeah. Okay. All right, good. So this is how it looks if the graphs are isomorphic. So if the graphs are isomorphic, there exists a strategy that lets players win. Right? Of course, not every strategy takes this specific form. However, without loss of generality, we can restrict to deterministic strategies. So where Alice's answer and Bob's answer only depends on this x or x prime that they get. Right? And in that case, you can see that a strategy is simply a pair of functions, right? One that takes vertices of G to those of H, and one for vertices of H to vertices of G. So you have two functions for Alice and two functions for Bob. And what you can show, actually, if these four functions together, if they form a winning strategy, so strategy that wins irrespective of this x and x prime, then you can extract a graph isomorphism. So essentially what you're going to get is that alpha is equal to beta, and alpha prime is the inverse of alpha. And it's going to be adjacency and non-adjacency preserving, so it's going to be a graph isomorphism. So what this says is that we can capture graph isomorphism using this non-local game. Namely, two graphs are isomorphic if and only if there exists a strategy that lets players win. Okay? And now what we can do is we can sort of just define quantum isomorphism or non-signaling isomorphism as the existence of a winning strategy in the corresponding class of strategies, right? So we would say that graphs are quantum isomorphic if there exists some quantum strategy that lets Alice and Bob win irrespective of the vertices received. And the same for non-signaling. Okay, and of course the game remains the same, right? All that changes is what strategies Alice and Bob have access to. And the way we can specify a quantum strategy is by a shared quantum state and some measurements that Alice and Bob are going to perform upon receiving X and X prime, right? Now they can try to use these measurement outcomes to sort of help them win the game. And without loss of generality, we can assume that the measurement outcomes are simply given by vertices of the graph. So the way Alice and Bob are going to play is they receive X, they perform the measurement E of X or F of X for Alice or Bob, and then they're going to respond with the classical outcome that they got as a result of their measurement. Okay, and now if they play according to this strategy, right, then according to the Born rule, like the probability that upon receiving vertices X and X prime, Alice and Bob respond with Y and Y prime is just given by this sort of inner product, right? So these are the two operators that Alice and Bob have applied. Okay, and again, we know, right, that these quantum strategies form a superset of classical strategies, so possibly more graphs become isomorphic with respect to this quantum isomorphism relation. And we would like to know for which pairs of graphs does there exist this perfect quantum strategy. Now, if you had some quantum strategy and that gave you this joint conditional probability distribution P, then we know that it always satisfies these so-called non-signaling conditions, right? We know that the this probability distribution, it cannot be used by Alice and Bob to send information from one to another. And mathematically, it's expressed by saying that these marginals are independent so Alice's marginal is independent from the question that Bob received. And similarly, Bob's marginal is independent from the question that Alice received. Now, a non-signaling strategy is simply any joint conditional probability distribution which satisfies these two conditions, right? So we don't require that this P is obtained as this inner product. It just satisfies these two linear conditions. And because we just have some linear conditions on our P, it's sort of usually much easier to check whether there exists a non-signaling strategy. All right, and then we define this non-signaling isomorphism as simply existence of a winning non-signaling strategy. So what that means is that we have some probability distribution P which has zeros in the spots which correspond to Alice and Bob losing the game, right? Okay, so now let's suppose that we have two graphs, G and H, and they are non-signaling isomorphic. So there does exist this joint conditional probability distribution P satisfying these conditions and with zeros in the right spot. Now, from such a P, let's define this matrix D. So the rows of D are indexed by vertices of G and the columns by vertices of H, and we simply set it equal to the probability that upon receiving vertices, when both players receive vertex G, they both respond with vertex H. And using these non-signaling conditions here and also the zeros, remember the P was winning, so it has some zeros, we can show that this matrix D satisfies two properties. Namely, it's doubly stochastic, so it means its entry-wise non-negative and its rows and columns sum to 1. And it also satisfies this commutation-like relation with respect to the adjacency matrices of two graphs. All right, so if G and H are non-signaling isomorphic, I can build this D with these properties. Now, it turns out that existence of such a D is already known and studied relation on graphs. Namely, it's called fractional isomorphism, right? So two graphs G and H are said to be fractionally isomorphic if there exists this D, which commutes through the adjacency matrices. Okay, so what I told you before, that says that non-signaling isomorphism implies fractional isomorphism. And actually, we were quite surprised by that. You can show the converse as well, so that whenever your two graphs are fractionally isomorphic, you can also find a non-signaling strategy. And in order to do that, we need to use a very nice theorem by Roman, Shireman, and Ullman, which characterizes this fractional isomorphism in terms of some very structured partition of vertices of the two graphs. Okay, but as a result, we get this theorem that says non-signaling isomorphism and fractional isomorphism are the same things. And we sort of saw roughly how the proof goes already. Okay, but because this fractional isomorphism is previously studied, we sort of get nice connections to other areas of mathematics. For instance, we know that non-signaling isomorphism is equivalent to graphs G and H not being distinguished by the so-called one-dimensional Weisfeiler-Lehmann algorithm. So this is a class of algorithms for trying to decide if graphs are isomorphic or not. So for every dimension you have one algorithm, and these algorithms, if this D is fixed, the dimension is fixed, then they run in polynomial time. And they are sort of very well known in this literature on graph isomorphism. And we also get a connection to descriptive complexity. So it says that non-signaling isomorphism is equivalent to saying that there is no formula in two-variable counting first-order logic that could be used to distinguish these graphs G and H. And as a corollary to these things, we get two things. So first, we can test non-signaling isomorphism in expected linear time. And this is because that is the runtime of this one-dimensional Weisfeiler-Lehmann algorithm. And non-signaling isomorphism distinguishes almost all graphs. So it seems like really nice. We have an efficient algorithm that works for graph isomorphism almost all the time. So the catch is sort of that sometimes it fails really miserably. So here are two graphs which are non-signaling isomorphic, but they're clearly not isomorphic, right? So the graph on the left has two components, the graph on the right has just one. So it's not the same graph, right? And more generally, this non-signaling isomorphism is going to fail to distinguish any pair of graphs that has the same degree and the same number of vertices. Okay, so now that okay, but as far for understanding this non-signaling isomorphism, we have sort of fully understood it. We've shown that it coincides with this previously known relation on graphs. Yeah. Just say whether or not they're isomorphic. Yeah. No. So it's a corollary of the fact that non-signaling isomorphic, like it's not something you should have seen right now. You can just use results that are known about isomorphism, and it tells you that it works for almost all graphs. Yeah. Okay. All right. So we've sort of understood this non-signaling isomorphism. So let's go on to, or go back to quantum isomorphism. Okay, just remember, right? So two graphs are quantum isomorphic if there exists this strategy that lets quantum players, using entanglement, win irrespective of the vertices they receive. Okay, the nice thing that we can show is that if there is some sort of strategy that lets the Alice and Bob always win in this game, then we can find a strategy of very, very special form. So in a general strategy, we don't know what this state is. It could be any state. For this particular game, we can show that the state always has to be maximally entangled. We don't know the dimension, but we know that the state is going to be maximally entangled. We also can show that the operators are projectors. So, I mean, you can always get projectors by sort of increasing your Hilbert space, but that's not what's going on here, right? Here, I'm restricting to the support of the state. And on the support of the state, the operators are projectors. In addition, sort of Alice's and Bob's operators are not independent from one another. You can show that Alice's okay, this is not what it says here. Okay, yeah. So Alice's operators actually give Bob's operator if you just take the complex conjugate of the corresponding operator. And also, if you change sort of question and answer, so if you ask what sort of these operators EXY and EYX, so this one corresponds to Alice getting vertex X and responding to Y, and this one corresponds to her getting Y, responding with X, those operators are the same. And now this kind of structure of winning strategies lets us get some sort of matrix-based reformulation of quantum isomorphism. So we can say that two graphs are isomorphic if and only if there exists this, what I'm going to call projective permutation matrix script P, which commutes with AG tensor identity and the same for AH. All right. So before I tell you what this projective permutation matrix is, let me just show you that this syntactically, it looks very, very similar, right, to how we can define, to the matrix-based formulations of graph isomorphism. So here I'm requiring that there exists a permutation matrix P, and fractional isomorphism, where I'm requiring that there exists a doubly stochastic matrix D, right? So syntactically, this thing looks very similar to these. Okay, but what is a projective permutation matrix? First, I want you to take a very special definition of a permutation matrix. I could say that the matrix is a permutation matrix if it's unitary and all of its entries are either 0 or 1, okay? Now, that the entries are 0 and 1, I can rewrite it just by saying that they square to themselves. And if I want, I can also add a relation that if I take xij star, so xij dagger, like the complex conjugate transpose, then I get xij, right? For numbers, for real numbers, it's not saying anything. All right. Now, a projective permutation matrix is the same thing, except that instead of these xij's being numbers, I now allow them to be matrices. But not any matrices, but matrices which satisfy xij square is equal to xij, and xij dagger is equal to xij. But this is the same as saying that these xij's are permutations. And I ask that, sorry, they are projectors. And I ask that all my projectors are of the same size, so some D by D orthogonal projections. All right. And if my D is 1, then I recover the definition of a permutation matrix. Okay, so that's why we called it projective permutation matrix. All right. Now, one easy corollary of this theorem, of this characterization of quantum isomorphism, is to see that it tells you that quantum isomorphic graphs necessarily need to be cospectral. Cospectral means that the adjacency matrices have the same multiset of eigenvalues. The way we can see it is, well, from here, right, because this script P is unitary, I can just rewrite this thing as conjugation by P gives me, conjugates AG tensor identity to AH tensor identity. Now, conjugation by unitary doesn't change the eigenvalues, and tensoring with identity changes the eigenvalues in a very predictable way, right? So from there, you can conclude that AG and AH necessarily have the same spectrum. Yes? So I'm not sure. This D And the size of these matrices xij, that's the same. Maybe we can discuss after. Okay, thanks. Okay, and sort of we recently realized, and this was also independently noted by Master, Reuter, and Verdun, that sort of this also gives a nice connection to the quantum literature on quantum groups. This doesn't have to do anything with quantum information. This is some area of mathematics that studies non-commutative algebras, I would say. And in that literature, these things, they would be called magic unitaries, except that these entries now would be allowed to be from some C-star algebra, so they are not necessarily just D by D orthogonal projection. Okay. Right, and sort of this matrix-based characterization of graph isomorphism and some other arguments help us to show that sort of if you have two graphs G and H, then, and they're quantum isomorphic, then actually there need to be some sort of similarities between the two graphs G and H, right? So it's not that these quantum strategies are so powerful that they're going to let Alice and Bob convince the verifier that any two graphs are quantum isomorphic. So for instance, you need that the two graphs have the same diameter and radius. They need to have the same number of connected components, same number of triangles, and more generally just the same number of walks and closed walks of some fixed length. Next, not only graphs themselves are cospectral, but actually their complements are cospectral, and they have cospectral Laplacian matrices. But actually all of these properties, they follow from the fact that the two graphs have isomorphic covariant algebras. And I'm not going to go into details about that. Yes. Okay. So now I've told you a bunch about this quantum isomorphism, but one thing I didn't tell you is, are there graphs which are quantum isomorphic but not isomorphic? Okay? And actually for us it was really hard to find such pair of graphs. Remember I told you, right, that this quantum value of a game, it's not computable. So perhaps it's not so hard to understand, right, that if I give you two graphs, it's really hard to figure out whether or not they are isomorphic or not, quantum isomorphic or not. Okay. So, but now we have sort of a general construction that lets us obtain such graphs. So sort of the idea is, what do you do when you don't know how to solve a problem? We'll take a different problem and reduce from it, right? Use the work that somebody else has done. Okay, and the class of games that we reduce from is known as binary constraint satisfaction games, in particular Parity, or sometimes they're called linear BCS games. Okay, so first, yeah. Yes. Well, I mean, if you have a non-signaling strategy, right, that doesn't imply the existence of quantum strategy. Quantum strategy implies the existence of non-signaling strategy, but not the other way around. Actually, the graphs I showed you, right, they had different number of components, and we know for quantum they need to have the same number of components. Okay, so yeah, it's not so easy. It's not so hard to find pairs of graphs which are non-signaling isomorphic but not isomorphic. But with quantum, things are much harder, unfortunately. Okay. So we look at these binary constraint systems. So binary constraint system is simply like a collection of monomials. Just let's look at the example. You have some variables. The variables take values, plus or minus 1. You have some equations on these variables. And you are asked, like what you want to figure out is there some sort of assignment of values to variables such that all these equations are satisfied. Okay, so actually this system I've written down here, maybe somebody already sees, it is not satisfiable. And actually it corresponds to this magic square game that maybe some people know. And the reason, the easy reason why it's not satisfiable is because if I multiply together all these equations, then every variable is going to appear exactly once. And on the right-hand side, I'm going to get 1. So the product of all the variables is 1. This is what these three together are saying. But if I look at these ones, again, every variable is going to appear exactly once. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I get -1 as the product of all of them, right? So it's -1 is not 1, so it can't be both. Okay, so this system is not satisfiable. But now we can look at this notion of quantum satisfiability. It can be defined through a game, or we can think of it, so this was introduced by Cleve and Metal, by the way. So we can think of it as sort of an operator solution to those systems of equations that we just saw. But our operator solution needs to satisfy some properties. So first, we require that our operators, so now we're going to assign operators to our variables rather than just plus minus 1, right? So we want that the eigenvalues of all the operators are plus minus 1. In other words, they square to identity. And also, we want that if you have two operators which appear together in some equation, then you want that they commute. And the physical reason is why you want that is because you will want to kind of think of these things as observables, and you will want to jointly measure them, okay? And for that, we need them to be commuting. Okay, and so now the same system that we saw before, so it wasn't satisfiable. However, it is quantum satisfiable, right? Because so if you know magic square, then it is because magic square has a perfect quantum strategy. And in fact, the matrices that we need to use are simply tensor products of Pauli's. And they're just some 4x4 matrices that are going to allow you to satisfy all these conditions. And of course, when I multiply matrices, I don't get 1, I get identity, right? So you should replace this 1 and -1 with identity and minus identity. So we know you can't have in dimension 2. I don't know if you can have it in dimension 3 or not. Maybe you can't, but yeah. All right. So and sort of so unfortunately, these operator assignments, they are very hard to find, and this is the same result by Williams-Lofster that I mentioned before. So this quantum satisfiability of parity BCS is not decidable. So we are happy if we find a satisfying assignment, but in general, if you ask, is there a satisfying operator assignment, that's a very hard problem. Okay, but remember we wanted to construct pairs of graphs, right? So let's see, how do we get a graph from a system of equations? So let me show you an example. So here I have two equations. One says that these variables multiply to -1, and these other ones multiply to 1. This is the graph that I'm going to build. So sort of these vertices, they correspond to this equation, and these vertices to this equation. It's labeled by a satisfying assignment of the corresponding equation. So for instance, if I put -1, -1, -1 to x1, x2, x3, then I get -1 as the product, right? And here I've listed the 4 satisfying assignments, the same here. Now, the thing is, this is not a full assignment, right? This is a partial assignment because I'm only assigning values to variables which appear in this particular equation, and that's very important. Now, how do I get edges? Well, I draw an edge whenever the two assignments are inconsistent. So, for instance, let's look at this edge here. Okay, so they are inconsistent if I'm assigning different values to the same variable. So the only variable that these two equations have in common is x1. So basically what I need to check is, are the first positions of these strings different, right? So here I have an edge because I have minus in the first position, and here I have plus. The same here. And we always have cliques, so complete graphs on the vertices corresponding to the same equation because they are different satisfying assignments for the same variables. So they differ in some position. Okay. Now this is one graph, but to talk about graph isomorphism, I need two graphs. Okay, so then what you do is you take your BCS, your system of equations, and you simply, so remember all the equations said equals to 1 or equals to minus 1. You replace all the minus 1s with plus 1s, right? So all your equations say some subset of variables multiplied to plus 1. Well, this is a trivial constraint system because I can always satisfy it by simply assigning value plus 1 to all the variables, right? Okay. But I'm going to call it sort of given a BCS F, this kind of trivial one, I'm going to denote it by F1. Right, always satisfiable. Now the nice theorem that we get is a relation between satisfiability and isomorphism. So it's not, so first, if my F is satisfiable with plus minus 1 variables, if and only if the two corresponding graphs, so I build one from F, one graph from F, and one from its sort of trivial version. If those graphs are isomorphic. And then I get the same thing for quantum satisfiability and quantum isomorphism. Right? And now, if we just take the example, the magic square, right? So it is this, the system is quantum satisfiable, but not satisfiable. So if I construct the corresponding graphs, then I get a pair of graphs which are quantum isomorphic because the system was quantum satisfiable, but they're not isomorphic because my system was not satisfiable with plus minus 1 variables, right? So this allows me to get examples of pairs of graphs which are quantum isomorphic, but not isomorphic. Okay, yeah, and actually we can get infinite family of examples this way. Another thing that this does, though, it shows that quantum isomorphism is undecidable. Because essentially what this theorem does, it gives a reduction from these parity BCS, from quantum satisfiability of parity BCS, to the problem of deciding whether two graphs are quantum isomorphic, right? And by by Slofster's result, we know that the first problem is undecidable. So the problem we're reducing to also must be undecidable. Okay, so just to show you the graphs that we get. So here are two graphs for magic square. Clearly not isomorphic, right? Everybody sees. Yeah. Okay. All right, just according to the theorem we show, these graphs are not isomorphic, but they are quantum isomorphic. So these are the graphs we get from magic square. There are graphs on 24 vertices, and this is the smallest example that we know so far. At first I thought that probably there exist much smaller graphs, but actually we can show a lower bound on the number of vertices, and it's somewhere around like 15 or 16. So, I mean, we are off 24 and 15, 16, but we are not as far off as I would have initially expected. All right, so let me just, yeah. 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 They are. Like every operator is gonna be one of these Pauli matrices or some kind of very simple matrix. Yeah. So the dimension like that you need to play this game is the local dimension is still 4. Okay. So let me just summarize what we saw. So we started by sort of thinking about graph isomorphism in terms of this interactive protocol where Alice and Bob tried to convince a verifier that graphs are isomorphic. And then we said, well, we can find a game that precisely captures isomorphism, Right, and then we looked at what happens if we allow more powerful strategies to Alice and Bob, what happens if we give them quantum strategies or non-signaling strategies. And then we saw that this non-signaling isomorphism actually turns out to be equivalent to a previously studied notion, namely fractional isomorphism, and it's therefore decidable in polynomial time, well, in expected linear time. We get the polytime decidability just from the fact that it was systems of linear equations for non-signaling isomorphism in general. Okay, and I guess one way you can view this result as sort of giving an operational interpretation to this mathematical notion of fractional isomorphism, right? As an existence of this non-signaling strategy in this interactive protocol. Right, and then we saw that quantum isomorphism can be, also admits sort of this matrix-based formulation that is very similar to the way we define isomorphism in terms of permutation matrices and non-signaling isomorphism in terms of doubly stochastic matrices. And this sort of formulation also provided the link to this area of quantum groups. Right, and then we saw a way how we can construct pairs of graphs that are quantum isomorphic, but not isomorphic. And this gave us these nice examples, but it also showed that quantum isomorphism is undecidable. Right, so sort of we saw these three different relations: isomorphism, quantum isomorphism, non-signaling isomorphism. Just because quantum strategies are more powerful than classical, non-signaling more powerful than quantum, you have this chain of implications. Okay, and we know that none of the converses hold. All right, so that's all I wanted to tell you. Thank you very much for your attention. You've been a great audience.
Yeah, thank you very much for this very didactic presentation of quite some exciting results. We had a couple of questions already, but I'm sure there's more.